Hello, everyone. Warm welcome to you from the Australian National University here in Canberra. My name is Jay. I look after international relations and partnerships here at the ANU in the areas of sciences, health, and medicine. Joining me today, of course, is Dr. Paul Lam Yeung, who will be telling us about wave propagation. Now, before we start, I'd like to acknowledge the Ngunnawal and Ngambri people who are the traditional owners of the land where ANU is located and where we are broadcasting to you today from. And I pay my respects to their elders, past and present. Now, let me very quickly introduce our speaker for today, Dr. Paul Lam Yeung. Paul Lam is a senior lecturer at the ANU Mathematical Sciences Institute, and his research here revolves around harmonic analysis and related areas, with a particular focus on singular integrals, Sobolev embeddings, time frequency analysis, oscillatory integrals, and Fourier decoupling. Paul Lam studied harmonic analysis at Princeton University, and after completing his PhD, he worked at Rutgers, the State University of New Jersey, at University of Oxford, and at the Chinese University of Hong Kong before coming to the ANU. Paul Lam has won many awards and fellowships for his research, including a Titchmarsh Fellowship from the University of Oxford, an Early Career Award from the Hong Kong Research Grants Council, and a Future Fellowship from the Australian Research Council. All right, without any further delay, I'll now hand over to Dr. Paul Lam to take us through some fascinating mathematical questions concerning wave propagation. Over to you, Paul Lam.
All right, thank you. Thank you very much, Jay. Can you hear me well?
Yes, it's good.
Good. Yeah, so welcome all. I hope you're all well. So I recognize I'm speaking to a very diverse audience here. I'll try my best to make it an enjoyable talk for everybody. Like Joy said, if you have any questions, please feel free to put it through the chat at any time. I'll try to get to it at the end of the talk. So today we're going to look at some two things that can happen as wave propagates through space. You may have encountered the interference pattern that you see on the front page of the slide here when you study physics. And we'll come back to this in a second. Yes. So for us, waves are just oscillations or vibrations that propagates through space. So think of that as sound waves or water waves or light waves or whatever. And today, one of the things that we wanted to see is how waves can possibly interfere with each other. So remember the interference pattern that we have seen on the previous page. It was produced by 2-point sources. But having only 2-point sources is, I would argue, in some sense boring. And mathematically, many more interference patterns are possible. So today, one of the things that we will look at are some mathematical patterns that can arise as waves propagate through space and interfere with each other. Along the way, we will see some fascinating questions about wave propagations, and I'll try to explain some recent efforts in addressing such questions. And despite much recent progress, some of these questions remain open, and we'll try to understand why. Some of the work is actually done at ANU here, so I hope I will also get a chance to highlight that as we get to it. Okay, so on this page, I have first written the wave equation in n spatial dimensions. It is the second time derivative of u reflected t equal to the spatial Laplacian of u, where the Laplacian is just the sum of the second order derivatives in the coordinates directions. Now, as a rule of thumb today, you can ignore most of the equations on the slides if you want to. If you haven't seen it before in particular, I'll try to explain things in a way that doesn't depend too much on the formula. But for those of you who have seen it, I thought I would just put them on so that it convey a little bit more information. Now, for instance, this wave equation here is the second order derivative in t of the unknown function u. So it is usually solved under two initial conditions. You tell me what the function is like when t is equal to 0, and you also prescribe the partial derivative of t of u reflected t at time t equals 0. So these are functions u0 and u1 of x, and if you give me these, usually you can solve the wave equation. Okay, Now, one fundamental fact about wave propagation in Euclidean space is that energy is conserved as wave propagates. And the energy is defined by this expression here. It is a spatial integral of some derivatives of u squared. Now, these derivatives are evaluated at the point x and t, and you integrate over x. So presumably this quantity, this integral here, depends on t. But the amazing thing about conservation of energy is that this energy is actually independent of the time t, if you obey the wave equations. And in fact, the energy at time t is just energy at time 0, which is given by, which is determined by the initial data. Now, for the moment, let's focus in a case where the spatial dimension n is equal to 3. So look at waves in 3 spatial dimensions. You could think of them as sound waves if you want. And we'll try to picture some solutions to the wave equation for t between 0 and 1. Okay. Yeah, so here we go. Let lambda be a very small positive number. Let's say lambda is 1/1,000,000, very small. Now imagine a small explosion in the air that produces an initial high pressure zone in a very small ball of diameter lambda at time t equals 0. So maybe something like this. Okay. This produces a single wavefront of thickness. There is one wavelength, which is lambda, and that is going to travel away from the source at the center at unit speed. So this is what's going to happen. You have a small explosion in the middle, in this red dot here, which is like a small ball in 3-dimensional space of diameter lambda. And then as time progresses, your initial explosion is going to, this disturbance is going to travel away from it. And the amplitude will decrease over time. So maybe initially at t equals 0, you have a disturbance at this red dot here. And now at time t equals 1, the disturbance spreads and it becomes the blue circle, the blue small thin spherical shell that you have in 3-dimensional space. And I mean, this is an attempt to draw a 3-dimensional thing in 2 dimensions. So you know, when I draw this blue circle, of course, what I really meant is a symmetric spherical shell centered at this red dot of, let's say, radius 1 and of thickness, let's say, lambda. It's a thin spherical shell. And one of the things you can try to do is to figure out the size of the solutions if you know something about it initially. For instance, if you happen to have arranged things so that initially at time t equals 0, the function u is of size approximately 1/lambda. So this is the size of the solution in this red dot at time t equals 0. It is approximately 1/lambda. Then if you use conservation of energy, you will be able to predict the size of the solution at time t equals 1. The absolute value of u is going to be comparable to 1 as time t equals 1. So on this blue shell, the amplitude is going to be smaller, much smaller than what you had at the origin at the beginning, because remember, lambda is a tiny, tiny number. 1/lambda is much bigger than 1. The solution just spread it out so that at time t equals 1, this solution is going to be concentrated on this blue shell, and that has size roughly 1 over there. So I actually see a quick question from the chat. Why is there like a thin spherical shell? Where does it come from? Yeah. So imagine, well, if you wanted maybe a 2-dimensional analog, this is easy to see. Just drop a stone in the pebble. Drop a stone on a pond of water. Then maybe you have one wavefront drawing out, and that one wavefront is what I've drawn as the blue spherical shell. So if you have a small explosion in the air, then the sound wave is going to spread, but the explosion just happened at one time, right? So it's just one explosion, and hence you have just one sound wave going out, and then it's just that's larger and larger and larger, and then it would concentrate along a spherical shell, but the spherical shell would get bigger and bigger as time goes on. Does that make sense? Well, thanks for the question. All right, let's come back to this. Yeah. So we just saw a solution to the wave equation that involves the spreading of a single spherical wavefront. But one feature of the wave equation is that it is time reversible. And by this I mean if you take a video of the solution that spreads out from the center, record it, and just play it backwards in time. Well, what you will see is still a solution to the wave equation. So if u of xt is a solution to the wave equation, then so is u of x comma 1 minus t. In fact, you can just plug this into the equation if you know the equation and verify that. So if you had initially like a wave that is concentrated on this blue spherical shell of with lambda, and then you just try to run it backwards. So let it go back to the center. Then maybe after time 1, this wave would actually concentrate back into the tiny red dots, the tiny red ball of diameter lambda that you started with. And then this would also be a possible phenomena that can happen with waves in three-dimensional space. So you could have waves concentrating into a tiny small ball as time goes on, if you arrange it correctly. Okay. Now, by the way, there's another question. The bandwidth, the wavelength is going to be just lambda. So since it is going to be supported in a small spherical shell, the wavelength is just lambda. Okay, so yeah. Now, this is one kind of behavior that you can have for solutions of wave equations. Let's look at another one. This one is also very physical. Imagine you have a loudspeaker with a diaphragm that takes the shape of a unit disc. Okay, so it is disc of unit diameter. If the diaphragm oscillates over distance lambda like this, just once, then maybe it can produce a high pressure zone that is concentrated along a thin cylindrical slab of diameter approximately 1 and thickness approximately lambda. So in fact, I have a little coin here. Well, if you take this coin, think of this as a diaphragm, move it a little bit, right? Then maybe it is going to produce a high pressure zone that takes the shape of a coin. And if you look at the coin sideways, what you see is basically just a straight line, and this is the blue straight line that I'm drawing down here on the screen. It is supposed to be like a three-dimensional picture, but again, it's when I project it down to 2 dimensions, I had to give up the round parts in 2 dimensions. Okay, so that's what the shape of this high pressure zone is like. Now this high pressure zone is going to travel as time evolves. So this is going to create a plane wave that propagates in a direction that's perpendicular to a diaphragm or perpendicular to the surface of this coin. And it is probably going to go at unit speed if we normalize the units correctly. So maybe it is going to go in this direction, and in time 1, it's going to reach here. And what happens for this one? Well, this one, the wave is not spreading, it is just moving along. And if the initial amplitude is, let's say 1 at time t equals 0, then the amplitude at time 1 is also roughly equal to 1. In fact, its amplitude is not going to change for t between 0 and 1. Okay, so these are sensible solutions to the wave equation that you can imagine in space. Now, one of the things you might wonder is what happens if the diaphragm is not a disc of unit diameter. What if the diameter d of the disc is actually smaller? So instead of this big coin here, maybe, do I have a smaller coin? I think I did, but I seem to have just lost it. Anyway, imagine a smaller coin, and you also create a disturbance by just having the diaphragm move a little bit. It will produce a plane wave that has a smaller diameter. So the smaller diameter would be d. Well, it is still going to travel in a direction that is perpendicular to this surface of the coin, and then in time 1 it's going to reach here. The amplitude is also not going to change. So that's what you would expect if you have just a slightly smaller coin. The only catch here is that the diameter cannot be too small. So if you take a really, really tiny coin, if the coin is so tiny, then you cannot distinguish the coin from just a point. So this is what I'm trying to say here. If the planar source has a diameter that's too small, then it might become a point. So if you have a point source, the solution to the wave equation should spread out, and this is not what we are seeing here. So a planar source is going to be different from a point source, and as a result, you can't take a planar source that has a diameter that's too small. Otherwise, you get spherical wavefronts, and you don't get a planar wavefront. All right, so it turns out that the threshold here is at the diameter d being equal to square root of lambda. Remember, we are always considering waves that has wavelength lambda. Lambda is a very small number. And the threshold is at the place where the diameter is square root of lambda. It cannot be that small. If you get smaller, then it becomes sort of like a spherical thing, and that's not good. But as long as the diameter is still like essentially square root of 1/2 and not smaller, then you will still get a plane wave. It will still travel in unit time to by a distance 1, and its amplitude will still remain roughly the same as time goes on, at least for time 1. Okay. And we're going to give such solutions to the wave equation a name. For every small lambda, a solution to the wave equation like this, a small plane wave with a diameter that is like lambda's the square root of lambda, and width that is like lambda. The solution to such a wave equation, if you look at its initial data, we are going to call it a wave packet. Okay. It's a tiny portion of wave that travels along a straight line in space. Okay, so this is like a wave packet that I've drawn here. Now, a wave packet is always going to travel in a direction that is perpendicular to the plane along which it is concentrated. It's a plane wave, after all. And we will assume that the amplitude of the wave packet is roughly 1. So the size of the solution, the absolute value of the solution, is roughly equal to 1. So that it travels through space. As it travels through space, the amplitude will still be roughly 1 for all t between 0 and 1. Okay, so these are wave packets, special solutions to the wave equation in 3 dimensions. Why are they useful? Well, for a second, let's try to use these to understand our earlier example, which I call the focusing example. Remember, we had this focusing example where we have wave concentrated on these blue spherical shell. The amplitude is going to be roughly equal to 1, and the thickness of this blue shell here is going to be lambda. We're going to let this wave concentrate. So it's going to move inside towards the center, and eventually it's going to end up at the center in a tiny red dot. Okay? But one of the things we can do is that instead of just this blue spherical shell, we can write the initial data, which is the blue spherical shell here, as superposition, or if you wish, sum of wave packets concentrated along these thin cylindrical slabs of diameter square root of lambda and thickness lambda. So this is like a wave packet. It has diameter square root of lambda, and the width of it is going to be lambda. We can have many such tiny wave packets. When you add them all up, you might be able to get the full blue spherical shell that we had at the beginning. Well, you can certainly do that. The question is, how many wave packets do you need in order to recover your original initial data in the focus example? So I'll let you think a little bit about it, and we'll talk about this in a second. Okay, it's essentially a geometric problem. Basically, remember each of these wave packets is actually a small cylindrical slab where the diameter is like lambda. So if you look at the like the circular parts of the coin, right, the surface here. The surface here is going to have area roughly pi times the radius squared. So it's roughly going to be, the area is going to be roughly lambda. And if the area covered by one wave packet is lambda, but now you have a unit sphere here, in order to cover that, you probably need roughly 1 over many small disks to cover this whole unit sphere. And as a result, when you try to just reconstruct your initial data using these wave packets, altogether you will need 1 over lambda many wave packets in order to make up your original initial data. Okay. So you have 1 over lambda many wave packets on this blue spherical shell. And it's going to concentrate, we know it's going to concentrate towards the origin at time 1. So after time 1, these 1 over lambda many wave packets, they would have all traveled to the center. So they are going to line up like this. Like they're going to line up in different directions. They will all reach the center. And at the center, they're going to produce a peak by constructive interference. Now remember, each of these wave packets has height roughly 1. And if they interfere constructively, and if there are 1 over lambda many of them, then the size of the solution in the middle would probably be roughly 1 over lambda. And this matches what we had before. So this is an alternative way of explaining why the size of the solution in the center should be roughly 1 over lambda if you started off with something that has size 1 on a spherical shell of radius 1. Okay. And a vague conjecture is that maybe this example, this focus example that we have, captures the worst case scenario of how waves of frequency roughly 1 over lambda can focus into a small tiny region. In fact, I would challenge you to try to come up with situations where waves get really concentrated in time 1 when they are really spread out at time 0. Like this is probably one of the most natural things that you can think of, right? Like just have waves coming from all possible directions. They all concentrate in a tiny ball. Maybe this is the worst that can happen. But in order to make sense of this conjecture, like in mathematics, we need definitions and formulations. So let's talk a little bit about how you could perhaps make sense of this, this conjecture. The first thing that we need is the notion of frequency, because in this vague conjecture, I've said that these waves have wavelength lambda or frequency 1 over lambda, and we've got to make sense of what it means. So it turns out that the Fourier transform with the relevant object to study here, this is the Fourier transform of a nice function on the screen here in n spatial dimensions. But never mind that. The main thing here is that the function, if it is nice enough, can be reconstructed from the Fourier transform, and it is actually a way of representing f as a sum of functions of the form exponential ix dot c. These are characters of the additive group Rn at c varies over Rn. So you take an average of all the characters they have on a group, you recover your function. Now, we say that f has frequency roughly 1 over lambda if one of the two things happen, the equivalent. If you know the Fourier transform, this is if the Fourier transform is going to vanish unless z has size comparable to 1 over lambda. So as long as z has size not comparable to 1 over lambda, f hat c is going to be 0. This is what it means for the wave to have frequency roughly 1 over lambda. Another way of saying that is that when you reconstruct f using this Fourier inversion formula, you only need all the z's so that the size of z is roughly 1 over lambda. It is a superposition of exponential ix dot c over z's with this constraint, and and you don't need any other characters for other z's. Okay, so this is what it means for a function on Rn to have frequency roughly 1 over lambda. And if you have a solution to the wave equation with initial data u0 and u1. These are functions on Rn. And if both of them has frequency roughly 1 over lambda in the sense that I've just described, then one can check easily that the solution u is also going to have frequency roughly 1 over lambda at every time t. So at every time t, you will have a solution that has frequency roughly 1 over lambda. And we say that u has frequency comparable to 1 over lambda. Okay. This is what it means for a wave to have frequency roughly 1 over lambda. Next, we needed to say what we need to measure how much wave have concentrated in space. And for that, we need a notion that measures the size of a solution to the wave equation. Okay, so what do we do? Well, a natural first attempt is to measure the size of a solution at time t by considering this spatial integral. You just take the p power of the absolute value of u and integrate over x, integrate over space, where p is some exponent that we'll talk about in a second. Okay, so this might be a sensible way of measuring how big your solution is. If your solution is really big, maybe the LP norm is really big in space. But this must be modified to take into account the time derivative of u. So it turns out the correct quantity to look at is the following, which I call EP of t. The precise formula is not very important, but this EP of t will indeed come up quite a number of times for the rest of the talk. But what is this? Okay, so well, for those who know what the square root of the Laplacian is, it involves the square root of Laplacian of the time derivative in u, and then you also take the LP norm of that in space. Okay, so that is what EP of t is. If u has frequency roughly 1 over lambda, which is the case we care about anyway, then EP of t is roughly just the integral of the p power of u plus the p power of lambda times the time derivative of u. You integrate this over space. So yeah, but never mind what the actual formula is. One of the things I would note is that if p happens to be equal to 2, then the quantity E2t is actually closely related to the energy of the wave equation that we defined like maybe at the very beginning. It turns out that E2t is also going to be invariant as time varies. It's going to be conserved as time changes. But this is not the case anymore if you take p to be bigger than 2. Let's say p equals 3, then this is not the case anymore. And EP of t, when p is bigger than 2, turns out to detect how focused the solution to the wave equation is at time t. And this is good because we wanted to try to see whether the focus example is the most concentrated solution that you can have for the wave equation at time 1. So this is a way of measuring how focused the solution to a wave equation is by looking at EP of t for the solution u. Okay, so this is the formula of EP of t again, but like I said, never mind what that is. It involves this p power of the u integrated over x. And what happens is that if u of xt is concentrated in this small region, a tiny, tiny region, then by conservation of energy, the solution has to become large in this very, very tiny region. Otherwise, the energy is not going to be lost, right? So the function has to be large at some point. And if it's concentrated in a very small region, the size of the solution is large over there. So if we look at the integral of the p power of u, remember now p is bigger than 2. You could split it as the integral of u squared times u to the power p minus 2. This term here, the u to the power p minus 2, is going to be large on a small region. But the integral of u squared is going to be roughly comparable as time changes. So if the solution is very concentrated at a certain time, then the second factor here is going to make this quantity huge, and hence EP of t huge. So EP of t is going to be large. We expect EP of t to be bigger than E2 of t if p is bigger than 2, and the solution concentrates in a small region in space at time t. Yeah, so in brief, if the solution concentrates in a small region in space in time t, And if P is also bigger than 2, then EP of T is going to be huge. Okay, so now let's look at some examples just to get an idea of what this is about. Let's compute, for instance, for our focusing example in 3 spatial dimensions, the values of E30 and E31. So in particular, I'm taking n to be equal to 3 in 3 spatial dimensions. The P, instead of 2, I'm going to take P equals 3. And I would compute E30 and E31. Remember, this is the focusing example that we have. It is initially very spread out, has size roughly 1 on this thin blue spherical shell. At time t equals 1, it's going to concentrate in the middle and going to have a huge magnitude over there. So if U is more concentrated at time 1, we expect E3 of 1 to be bigger than E3 of 0. Okay, so because U of x1 is concentrated in a small region, the red dot here. Let's see whether that is the case, just to convince you that this is a reasonable thing to do. Okay, so we're going to compute E3 of t, but let's cheat. In fact, in this case, it turns out that the second term is not relevant. It is comparable to the integral of u to the power 3, so let's just compute it. And it's not so hard, because if you look at the integral of u to the power 3, and let's say you're at time t equals 0, okay? So you're concerned with the blue spherical shell. What happens? The solution, u, is going to be roughly of size 1 over there. So if we take u cubed, it is roughly 1 to the power 3. But in order to calculate this integral, you also got to calculate the measure of the size where u of x is non-zero, which is the volume of this blue spherical shell. This blue spherical shell is going to have volume roughly lambda, because it has width lambda, but then it has a surface area roughly 1. So when you multiply these together, E3 of 0 is roughly lambda, which is a tiny, tiny number. Remember, lambda is like 1 over a million. Whereas if we compute E3 of 1, and let's see what happens. Well, u of x comma 1 is going to be roughly like 1 over lambda in this tiny red dot. So when you raise it to the power 3, it is 1 over lambda to the power 3. And then you have concentration of this solution in a tiny red dot that has diameter lambda. So the volume of that is roughly lambda to the power 3. When you multiply, you get 1, which is much bigger than E3 of 0, which is lambda. Okay, so that confirms our intuition. Like, you know, if the solution actually concentrates a lot, then E3 of 1 is going to be bigger than E3 of 0. And in particular, in this focus example, E3 of 1 is going to be bounded by this huge number, 1 over lambda, multiplied by E3 of 0. It is going to be much bigger than E3 of 0, and the inequality that you get is this one. The question now is this true for all solutions with frequency approximately 1 over lambda? So this is captured in the conjecture here. Is it true that for every solution u to the wave equation in 3 + 1 dimensions with frequency roughly 1 over lambda, that's E3 of 1 is bounded by 1 over lambda times E3 of 0. If this conjecture is true, that means that the focus example here is already one that almost achieves the worst case scenario they can have. It is a scenario where the left-hand side is roughly equal to the right-hand side. So this is essentially the worst possible focusing that you can have. And it turns out that this conjecture is true. It's been known for a while, since the 80s. Perel and Miyachi independently proved that the conjecture holds. If lambda is a tiny number like 1 over a million, and u is a solution to the wave equation with frequency roughly 1 over lambda, then E3 of 1 is going to be bounded by 1 over lambda times E3 of 0. In fact, there's a corresponding conjecture in all dimensions, and I encourage you to try to formulate that. It will be a fun exercise. And that was also settled by Perel and Miyachi. Okay. Now, about 10 years later, Seeger, Sock, and Stein proved the same result for a more general class of wave equations. Basically, they are wave equations through smooth, inhomogeneous medium. So think of X-rays passing through your body. You have tissues with various densities, and that is smooth and probably inhomogeneous because the density will vary. And just last year, right at the ANU here, Dorothy Frey, Pierre Portal, Andrew Hassel, and Jan Rosendahl, the two groups of researchers, they proved similar results for two even more general classes of wave equations. This time about waves through some rough inhomogeneous media. So maybe like you have porous rock that has very rough densities, but changing from place to place, and you send some ultrasound through it, then there will be waves through some rough inhomogeneous media. And yeah, so this is two groups of researchers that we have at ANU here. This is in fact in turn based on a new function space that was introduced by Hassel, Portal, and Rosendahl 3 years ago. That is particularly suited to the study of solutions to various wave equations. So if you are interested in functional analysis or harmonic analysis, these are very interesting function spaces, in my opinion, to study. This is built upon earlier work by Hart-Smith in 1998. Okay. Now, next we are going to look at the focusing example just once more. And one thing that if you think about it a little bit, you realize that the solution doesn't stay focused for very long. It stayed focused until time 1, like at time equals 1. Well, it is very focused, but then as time increases beyond 1, it is going to spread again, and it's going to become a thin spherical shell again. In fact, this is what happens for most of the times between 1 and 2. For most of the time, t between 1 and 2, this is a picture here, the blue spherical shell is going to get larger and larger, and the solution spreads. So for most of the time t between 1 and 2, the solution u of xt is not very concentrated. So even though E3 of 1 is much bigger than E3 of 0, if you take the time average of E3 of t, where t ranges from 1 to 2, the time average is not much bigger than E3 of 0, it's just comparable to it. And this leads to something called a local smoothing conjecture by Sorg, which in spatial dimension n equals 3 states the following. The time average of E3 of t, as t between 1 and 2, is not much larger than E3 of 0. It could be larger by 1 over lambda times epsilon, but the epsilon can be chosen to be arbitrarily small. And this is true for all solutions to the wave equation with roughly frequency roughly 1 over lambda. Okay. So it can be a little bit worse than what you have in the focus example, but not much more. It is necessary to put in this epsilon, but we will see why in a second. In fact, if epsilon equals 0, you see that you have this behavior here, but we can't take epsilon to be equal to 0. There are worse examples than that. And this time there's a real open conjecture in dimension 3. We'll see why, because there is a deep connection to some incidence geometry problems. So to see one such example, why this conjecture is hard, let's try to build something that I call a Wavetrain. What we do is that we pile up a bunch of initial data. These are wave packets. They're all traveling in the same direction. And this is what I call a wave train. Okay? So pick lambda is really tiny. You have wave packets of diameter 1 over lambda, square root of lambda. Align many of them in the same direction. This may be of height, let's say 2. And then send all of them to move in the same direction. This is what a wave train is like. And instead of drawing many blue solid rectangles, I'm going to just draw one big blue rectangle here that represents a wave train. Okay? So what you can do is the following. We may put together many wave trains. So at time t equals 0, put together many wave trains. They are concentrated in disjoint cylinders T of diameter square root of lambda, height 2, at time t equals 0. And all these travel in square root lambda separated directions into a unit square. So they are all in a slightly different direction. The angle between any two of them is going to be at least square root of lambda. They all enter this unit square, this black square that I've drawn here. Okay. Now, for any time t between 1 and 2, what would happen? Let's see, right? Like this is what happens when t is equal to 0. The wave would move, t equals 1. The wave have already entered the square, about to leave, and t equals 2. These wave trains are about to entirely exit the square, but not quite yet. So we look at that for every time t between 1 and 2. Let's look at this again. T equals 1, t equals 2. Each wave train is going to occupy a fixed cylinder t tilde of height approximately 1 in the unit square, like this. So let's say t tilde. These red cylinders. These are these will be occupied by the wave train for any time t between 1 and 2. And the upshot here is, of course, that these red cylinders overlap a lot inside the square, as opposed to the blue cylinders, which are disjoint. So we have this picture here again, can be arranged so that these t tildes overlap a lot more than the initial t's, which are disjoint. In particular, if we look at the volume of the space that is occupied by the red cylinders, t tildes, the volume is going to be much smaller than the volume of the total volume occupied by these blue cylinders, which are disjoint. Even though by conservation of energy, the integral of u of x Thomas 0 squared over these blue rectangles is comparable to the integral of u of xt over these red cylinders as t ranges from 1 to 2. So what happens is that the waves initially are very spread out. Now they become very concentrated on these red cylinders. And this is true for every time t. E3 of t is going to be much bigger than E3 of 0, like square root of log of 1 over lambda. Remember, 1 over lambda is really big. This is true for every time t between 1 and 2. It is a little bit weaker than what you had in the focus example because you have a log here. But this happens for every time t between 1 and 2. And as a result, if you average over time, E3 of t has a time average that is much bigger than E3 of 0 by a factor that's like square root of log of 1 over lambda. So I haven't told you how you construct these cylinders, but there's a way in incidence geometry to construct these things so that they overlap a lot over here inside the square. And this is really the problem. What if we can produce another pattern of thin cylinders in R3 that point in separated directions, but overlap even more than the previous example? Then we might be in trouble. Because the fact that they're pointing in separated directions means that you probably can produce some wave trains over there, run them backwards so that they don't overlap at all. And then if these wave trains all go inside this, this region where the thin cylinders overlap a lot, then you might have a high concentration of your solution to your wave equation for a long time. And that might produce a counterexample to the local smoothing conjecture. So this reveals a deep connection to incidence geometry, and this is why this is hard. In particular, in order to prove the local smoothing conjecture, we will have to rule out the possibility of having lots of thin cylinders in R3 that point in separated directions, but overlap significantly more than the previous example. And this is the contents of a famous conjecture called the Kakeya conjecture. One form of it states that if you have any collection of cylinders in R3 with diameter square root of lambda, very tiny diameter, and height 1, and let's say they point in square root lambda separated directions, then they cannot overlap too much. The Julian has measured at least lambda to the power epsilon for every epsilon. The interest here is for epsilon small. If epsilon can be taken to be 0, then there's a saying that the Julian of these tubes, these cylinders, must have measured at least 1, which is huge. But this is not quite strong. It just says that it has to be bigger than lambda to epsilon for any positive epsilon. Now, this is an open conjecture as well, and considered very difficult, despite much recent progress by many very good mathematicians, Kastel, Heckman, Rogers, Zhang, building upon earlier work of Bourgain, Wolf, Katz, Gould, and Tao. And it explains why the local smoothing conjecture is hard, because if you do have local smoothing conjecture, then you obtain automatically a proof of the Kakeya conjecture. And there is a locus moving conjecture actually for every spatial dimension n bigger than or equal to 2. We were talking about dimension 3, but there's a conjecture for every dimension. And then there's a relevant difficulty in every possible dimension from incidence geometry. That difficulty is understood in dimension n equals 2, like going back to the 70s, a long time ago. But still, it takes a non-trivial effort to establish the locus moving conjecture in 2 spatial dimensions. And this was done, but only very recently, 2 years ago, by Gu, Wang, and Zhang. Okay. So I see that I've been going for a while now. I thought I would quickly try to draw this to a close. But I would like to still make some more connections here. One of the things is that like in 3 spatial dimensions, even though you can't prove the full locus moving conjecture, sometimes you can prove something weaker. And this has been done, for instance, by Wolf in year 2000, by Bourgain and Demeter in 2014, never mind what this actual estimate is. The key there is in understanding how waves traveling in different directions can superimpose. And the tool that they use is called Fourier decoupling inequalities. They try to capture how waves will interfere when they travel in different directions. And such ideas somehow have some very surprising connections to number theory. Let's skip this. So this is the problem from number theory. We can look at a Diophantine system of n equations and 2s unknowns as such. Okay, so the first equation is a linear equation, the sum of the first s variables being equal to the sum of the last s variables. The second one is a quadratic equation. You replace sum of the variables by sum of squares on both sides. The third one is a cubic equation and so forth. Okay? So this is a system of Diophantine equation with n equations and 2s unknowns. Let's say all the unknowns take value between 1 and capital N. Then of course the system here has at least n to the power s solutions, because you can just choose x1 up to xs in any arbitrary manner between 1 and n. That would give you n to the many s choices of x1 up to xs. And you just require xs plus 1 to match x1, xs plus 2 match x2, etc. Okay, and Vinogradov conjectured that, well, this is really old, like going back to the 30s, that the number of solutions is at most n to the power s plus epsilon, if 2s is the number of equations little n times the number of equations plus 1. And this is not to be true if you have only one equation or a system of 2 equations. It turns out to be a very important conjecture because it implies something about the zeros of the Riemann zeta function. It also has consequences about estimates for exponential sums that people care about in the study of Schrodinger equation, etc. And only in 2014, Woolley has established this conjecture in when you have 3 equations in n equals 3, using methods of number theory. But the surprise came a year later when Bourgain and Demeter and Groove settled this conjecture in full for all n bigger than or equal to 4. So you can have any number of equations and you still have Vinogradov's conjecture. The tool that they use is somehow surprisingly really related to what we were talking about today. Wave packets, or more precisely Fourier decoupling. And this is a surprise because this is really a number theory problem, but the tools that they use really don't see much number theory, like wave packets, like incidence geometry. How can they tell you anything about numbers? But turns out they do. So inspired by this proof, Woolley has proved this same conjecture again, using this type of methods really from number theory. But the driving force was really from this Fourier decoupling, like from 2 years ago. And then, yeah, so Guo Li, Soren Kramnik, and myself use these ideas, and we have been able to prove certain Fourier decoupling inequalities just 2 years ago as well. But this time avoiding use of incidence estimates. Okay, so time is running up, so let me just summarize. Today we've seen that considerations regarding wave propagation in RN revealed surprising connections to incidence geometry and Fourier analysis. Actually, also a little bit of number theory, these ideas have been used to study problems from number theory. But then there are still many exciting and fundamental conjectures that remain open regarding wave propagation, or incidence geometry, or number theory for that matter. And this is still very much an active area of research, attracting efforts of many very good mathematicians. So I think some of you are probably undergraduates thinking about doing like a further degree. And I hope in this talk, I've given you also a little bit of ideas what kind of research projects we are interested in at the ANU. Regardless, I hope you have also enjoyed this talk. Yeah, so thank you for sticking through. Yeah, I'll hand it over to you, Jay. Thank you.
Fantastic. Thank you very much, Pauline. That was a very informative talk. We're open for questions now. So those attending, if you have any questions, please put them through the Q&A box. We've got some time to take questions. And I think they're starting to come through now, Pauline, so I'll let you take them and then start answering them. So.
Okay, the first question, what was the function space used by Portal, etc. in their 2018 paper? This is some sort of Hardy spaces, but adapted to the solutions to the wave equation. In particular, you've got to take into account that solutions to the wave equation can travel in different directions in space. You've got to separate this function into wave packets that would travel in different directions, measure the size of each of them, and then combine them together just to get back a size of your initial data. So that is the function space they use. But yeah, maybe yeah, I could tell you a little bit more about that later on. Yeah, it'd be too technical to write anything down here. Yeah, any further questions?
I understand there are some students sitting in a lecture hall listening to us. So whoever is sort of joining and projecting this on the lecture theatre screen can perhaps put the questions in on behalf of the students.
Why is this problem related to the Riemann zeta function? That's a very good question. I have, to be honest, only very limited understanding about this as well, because I'm not primarily a number theorist. I'm more like a harmonic analyst. But it somehow tells us about regions of the Riemann zeta function where you have no zeros. And the mechanism, if I remember well, seems to have to do with estimates for exponential sums. But yeah, that is as much as I can sensibly say at this point. Okay, any further questions?
We'll give everyone maybe a couple of minutes to put their questions in. If there's no questions, we may even finish on time.
Yeah, I believe the recording will be made available, and if you want to revisit that, you could do that at some point. It's easy to find my contact email on my webpage. So if you have further questions, I would also be happy to answer that.
Absolutely, yeah, please do. I mean, you can find Paul Amsterdam on the ANU webpage. You can also find a link to his research group,
yes,
the areas that he's part of. And
we do have a very active analysis and geometry research group at the ANU. So for those of you who might think about doing an honors or master's degree with us or PhD degree with us, yeah, I encourage you to give us a thought.
Fantastic, cool. But look, I think that's good, Paul. Thank you very much on behalf of all of those attending and tuning in. Thank you for that talk. It was great hearing from you. For all those that did come in and ask questions, thank you so much for tuning in. We do have a few more of these guest lectures and talks to go for the rest of this month, and also some in July. So if you haven't registered for them, please do. You can find details on the website. So please go have a look and do register, and we'll see you at one of those. We're back tomorrow, where Professor Jagadish will talk about semiconductor nanostructures. So particularly for optoelectronics. For those of you that are interested in nanostructures and nanomaterials, physicists, please do tune in. And we'll see you then. Thank you once again, Paul M, and thank you everyone for coming in. And have a great rest of the day.
Everybody. Take care. Bye-bye.
All right, great. Bye-bye.